Yeah. Okay, that's probably good. Yeah, so welcome back to Top 330. So as usual, to get started, let me give you an Italian expression while people are settling down. So the Italian expression of today is the following. Let me just minimize this and then put it there. It's the following. So if you speak some French, then you might be able to translate this directly. So the Italian expression of today is mangiare la foglia, which the literal meaning of which is to eat the leaf, as in a maple leaf or a leaf from a branch. Okay. But the figurative meaning means to understand quickly. So to understand quickly. So now, how can I use this in a sentence? Where's my sentence? Okay. I'm sure you're all wondering, how can I fit this into an educational context? So here's the sentence. Cesare hopes that his explanations today will help his 330 students mangiare la foglia. So I hope you can eat a lot of leaves today. Okay, good. Moving on. So today's lecture is going to be about the Myhill-Nerode theorem, which was originally proved by John Myhill and Myhill-Nerode. I have a nice anecdote about Myhill-Nerode, which I'll give sort of towards the latter half of the class, because I think it's a fun story. And we're essentially just going to be continuing our discussion of minimal DFA, because we'll see towards the end of class that the Myhill-Nerode theorem allows us to prove that minimal DFA are unique. So in other words, we saw on Tuesday, what's the problem? Is the recording running? Yes, it is. Thank you, Louis. Thank you. Yes, thanks. So what did we see on Tuesday? On Tuesday, we saw the minimization algorithm. So the minimization algorithm, what it did, let me come in front of you so you can see my legs. You could have a DFA, any kind of DFA, maybe it has redundancies, and then you give it to the minimization algorithm, so the minimization algorithm, it takes the DFA, and then it outputs a minimum DFA, right? So it outputs a minimum DFA such that the DFA I have here can be reduced further. So you can't have a smaller DFA, because if you did, then it wouldn't accept the same time. Okay. So now you might be thinking, okay, well, so there's the minimization algorithm, and then I have a bunch of DFAs which accept the same language. So maybe this is one DFA, and this is another. So I'm the DFA, I know you'll be getting this down. And then this is the minimization algorithm. Okay. It turns out that whatever DFA you give it, as long as it accepts the same language, the output is going to be the same. Okay. And that's actually quite useful. It's going to be very useful because we're going to see at the end of class that we can use that fact to create an algorithm which checks, for instance, whether two regular expressions describe the same language. Okay, but before we get to that, I need to give you a bit of background knowledge. So I'm going to start with a few recalls, and then I'm going to give you a bit of facts. I'm going to define two new equivalence relations, and then I'm going to define a new property about those two particular relations. So the first thing I just want to do is I want to recall, I'd like to recall what a equivalence relation does. So given some set X, and an equivalence relation R on X, we say that R partitions X with its equivalence classes. Okay, so pictorially, what does that mean? That means that imagine this is X, this is my blob X, okay? And I have some equivalence relation R on it, R. So what R is going to do is it's going to partition the set X. So maybe this is one partition, this is another partition, this is another, and this is another. And each of these partitions can be represented by equivalence classes of R. And all of the equivalence classes together, when you take their union, gives you the set X. Okay, and the other thing, because it's a partition, is there isn't any overlap between the equivalence classes. Okay, and so now that you have that sort of refreshed, let's define a new, I wouldn't say property, but a new, I guess you could say property of equivalence relations. So suppose I have a set X and an equivalence relation on X, let's call it R. Then the index of R is its number of equivalence classes. Okay. So for instance, in this case here, I have an equivalence relation R on X. So the index of R is 1, 2, 3, 4, 5. So here the index of R is 5. Okay. So that's the definition of an index. Now, there's a new property that some equivalence relations can have, and it's going to be very useful to introduce it now because then it comes up again when I talk about the Myhill-Nerode theorem and when I talk about the proof of the Myhill-Nerode theorem. So what is this property? Suppose I have a non-empty alphabet and an equivalence relation R on the set of all strings sigma star. Then we say that R is right invariant. If, and so this is a definition if, so really it's an if and only if, the following holds: for every pair of strings, x, y, and sigma star, if x and y are related through R, then this implies that for any string z, if you stick z to x and you stick z to y, then these two new strings will also be related. And so this makes sense if you think about what right invariance means. Right invariance means that you're invariant to anything that's at your right. So if I take any pair of strings and I add anything to their right, then they'll still be related. So that's all it's saying. All right. So now, the next thing I'm going to define and introduce is a new relation, which is going to be, it turns out, an equivalence relation, which is right invariant. But before that, yes, question. Yeah, absolutely, yes. So it must be the same Z. Yeah. That's why we didn't say, Z and U, right? Yeah. Okay. So now let's introduce a new relation, which is going to turn out to be an equivalence relation and also right invariant. So I'm going to denote this relation R sub M. You'll see why in a second. Let's fix a DFA M, which I'll write out explicitly. I think in this case, I'm going to use the start state as Q0, but S0 would have been just as good. Now we say that two strings, so this is a relation on strings. Two strings are related via R sub M. So two strings X, Y are related via R sub M, if and only if, when the machine starts at the start state and it reads X, and when the machine starts at the start state and it reads Y, these two destination states are exactly the same. So that's what this relation is saying. It's saying that two strings are related if, when you give them to the machine M, they end up in the same state. So one thing that I'd like to mention is that this is different, right? So note the difference. Note the difference with the squiggle relation we saw in lecture 8, so on Tuesday. So note the difference with P squiggle Q. So this was a relation on states, right? So it related states together. So that's the first difference, right? This other relation here is on strings, but this one is on states. Well, that's the major difference, really. So note the difference with P squiggle Q. So this relation was, this was a relation on states of a machine. Okay. Good. So now it turns out, so let's remark the following two things. The first thing, it turns out that R sub m is an equivalence relation. So R sub m is an equivalence relation. I will not prove this. Please check it yourself. The second thing, which I will prove, is that R sub m is right invariant. Okay, so this is good because we just introduced this definition of right invariance. So this is going to help you sort of internalize it. So remember what right invariance means. It means that if I have a pair of strings which are related and I stick any string to the right, the same string to the right, then those two other strings should also be related. Well, let's see if that happens. So suppose I have a pair of strings, x, y, and sigma star. And suppose that x is related to y via R sub m. So what does that mean? That means that I must have some machine M, right? So I have this machine M. I have a start state. And then what does it mean for x and y to be related through R sub m? It means that when M reads x from x, when M reads x from q naught, sorry, then it ends up in some state q. But then when M reads y from q naught, it also ends up in the same state, right? That's just by definition. Okay. So now let's see what happens when you stick a string z to both x and y. So let's pick some string z in sigma star. And now let's stick it to x and let's stick it to z. Well, in the machine, what will happen is from q, the machine is going to then read z, right? And it will end up maybe in some state p. But now notice, it doesn't matter what the string was for the machine M to get to Q. Whatever it was, once it's at Q, it's certainly going to, when reading Z, go to P. Right. So what that means in general then is that if you give the machine the string XZ and YZ, it'll end up in the same state, right? So what that means is that from Q0, if you read XZ, and from Q0, if you read YZ, then these two states are the same. Okay. Well, what does that mean by definition? That means that XZ and YZ are related. And that shows you why it's right invariant. Good? Yeah? Yeah. Yeah. Because why? So the question was, do we assume that after we attach a string Z, there's always a state the machine goes to? Yes, because DFAs are designed such that they can intake any string, right? So whatever string you give a DFA, it's going to end up in a state. Yeah. Good question. Good. Okay. Let's see. I usually only look here. Let me look at the sides. The sides look okay. All right. Good. Okay. Great, excellent. So the next thing I want to do is I want to define another relation, which is also going to be an equivalence relation and which is also going to be right invariant. But this relation has a special name. It's denoted sort of this triple horizontal line sub L, and it's actually called, you'll see why in a second, the Myhill-Nerode relation. So for the rest of the class, unfortunately, I'm going to have to keep saying the Myhill-Nerode relation, which is very cumbersome, but what are you going to do? Let me give the definition and then I'll get to you. Okay, so what's the definition of this relation? Suppose I have some non-empty alphabet and I have some language L defined over this alphabet sigma. So note the first thing to note here is that L is any language. So it could be regular, but it could also be not regular. Okay, so I have that set up. I have some language over the alphabet sigma. Now, suppose I have two strings. I have two strings xy in sigma star. Then I say that x is related to y via the Myhill-Nerode relation if and only if the following is true. For any string z in sigma star, if I stick z to x, and if I stick z to y, if xz is an L, then it implies that yz is an L. And if yz is an L, then it implies that xz is also an L. So this is the definition of the Myhill-Nerode relation. Now, a question for you. Let's try to think very hard about this. Does this relation look familiar? Please say yes. Why does it look familiar? Yes, it was in assignment 1, question 2. Very good. So in assignment 1, question 2, you actually proved that this relation, well, hopefully you did it, that this relation, so I'll remark this, the Myhill-Nerode relation is an equivalence relation. So in this case, you don't even need to check it. You did it yourself on assignment 1. The other thing, it turns out, is that this relation is also right invariant. So this requires a slightly more, I would call it step-by-step proof. Not rigorous, because the other proof was just as rigorous, but it requires a more step-by-step proof. So the claim here is that this relation is right invariant. This relation is right invariant. So let me prove this to you. The proof, right? Suppose I have a pair of strings x, y, and sigma star. And suppose that x is related to y via the Myhill-Nerode relation. Okay. Now, to show that this relation is right invariant, I need to stick some arbitrary string z to x and some arbitrary string z to y, so the same string. And I need to show that xz and yz are also related via the Myhill-Nerode relation. Okay, that's what I need to do. So let's pick some z and sigma star. What I want to show, right? So what I want to show is that xz and yz are related via the Myhill-Nerode relation. That's what it would mean for this relation to be right invariant. Okay, well, what does this really mean, right? By definition, what does it mean for these two strings to be related? So equivalently, what I'd like to show, or what I want to show, is that for any string I stick to xz and yz, let's call that string u. For any string that I stick to xz, and for any string I stick to yz, those two strings being the same, if this string is an L, then this string is also an L, and vice versa. Okay. So that's what I need to show. Right, that's just by definition. Okay, so how do I do that? Well, in this case, let me do a forward direction because the backward direction is exactly the same. Really, you could also do this proof like just in an if and only if, but to be explicit, let's just do the forward direction. So what is the forward direction? Well, the forward direction has to assume this part of the statement. So let's assume this. So let's assume that xz u is an L. Okay. Well, what do I know about concatenation? Well, because here I have my strings, right? I have my strings x, z, and u, and these are concatenated together. So let's see, I know that concatenation has an identity element that doesn't really help me here, but I also know that it's associative, right? So I know that concatenation is associative, which means that this string is exactly the same as this string, right? So this implies this by associativity. Okay, excellent. Now, I know that I have a string x, and now I've stuck some string zu to x. Okay, so what can I do next? Anyone want to help me? Yeah, Owen? Very good. Yeah. Relation. Absolutely, I agree. Yes, very good. Excellent. Excellent. So the comment is, well, zu is just some string, right? And I know that, where is it? I know that x and y are related via the Myhill-Nerode relation, but by definition, that means that if x plus some string that I stick to X is an L, that means that Y plus that same string that I stick to Y is also an L. Right? That's just by definition. So this is by definition of the Myhill-Nerode relation. Very good. And now I can just use associativity again, but sort of backwards, right? So I can just say, well, this also implies that YZ U is an L. And this completes the forward direction, right? Because I've taken some arbitrary string U, and I've stuck it to XZ. I've assumed the premise, and now I've shown the conclusion. And so that completes the forward direction, and the backward direction is exactly the same. So this is the backward direction, and this is the same. Good. So that completes the proof. So I can use a little box. Good. Excellent. All right. So now we're ready to state the Myhill-Nerode theorem. Are there any questions before we do that? Yeah. Okay. Yeah, so the question was, does that mean that XZ and YZ don't have to arrive at the same state? Yes. In particular, what I mentioned at the beginning is I said that L could not be regular, right? So if L is not regular, there isn't a machine that allows XZ and YZ together. Yeah. Very good. So that's why I really want to emphasize the fact that L doesn't necessarily have to be regular. Good, very good question. Excellent. Okay, people are with me. More so than on Tuesday, at least for now. That's great. Okay, good. No more questions. Good. All right. So at this point, I'm ready to state the Myhill-Nerode theorem. So the Myhill-Nerode theorem, which I'll just write MN theorem, has the following setup. So given some alphabet, which is not empty, and some language, which is a subset of sigma star, the Myhill-Nerode theorem says that the following three statements are equivalent. So in other words, we have if and only ifs all across. So what are these three statements? The first one is that the language L, so L is a language, and so the language L is accepted by some DFA M. Okay, so in other words, we have some DFA M for which the language accepted by M is equal to L. So in other words, L is regular. So that's the first condition. Now this condition is an if and only if with the second condition or the second statement. Yeah, it's more a statement, not a condition. So the second statement is slightly longer, but it's going to be okay. I'm going to explain it. But this is the statement. L is the union of some of the equivalence classes of some right invariant equivalence relation R of finite index. So noticeably longer than the first statement. So in other words, I have one if and only if two. And then the last part of the Myhill-Nerode theorem says that 2 is in an if and only if with 3. And so what's 3? 3 is that the Myhill-Nerode relation has finite index. Okay, this is what the theorem says. At this point, this probably looks like gibberish to you. When I first saw it, it looked like gibberish to me. So how do we un-gibberish it? Well, let's use pictures because I like pictures. So what I'm going to do is I'm going to show you what each of these statements are saying, and then we're going to prove each of the equivalences. So the first statement is very easy, right? It's just saying I have some language, which is a subset of sigma star, and I have some DFA M, for which the language accepted by M is L. That's the first statement, right? The first statement, very simple, very straightforward. The second statement, which is less straightforward, says that I have some relation R, okay? And R has some properties, right? So what are these properties? The first one is that it's an equivalence relation. The second one is that it's right invariant. And the third one is slightly more complicated. It says that you take some of the equivalence classes of R, you take their union, and that gives you L. So for 3, I think it's much easier to just represent this pictorially. Suppose I have sigma star. I know that R is an equivalence relation, so I know that R partition sigma star. So partition sigma star like this. And so this third property just says that take some of the equivalence classes of R. So maybe take this one and this one. Okay. Then L, right, this language L from here, L is just the union of this partition and this partition. That's what 2 is saying. So it's not so bad when you see it pictorially, I think. Right? And then the last thing, the third statement, whoops. The third statement is also not that hard to decipher. It just says that I have this relation, the Myhill-Nerode relation, and well, I know that because it's an equivalence relation, it has equivalence classes. So it has maybe this equivalence class, and so on. But at some point, the number of equivalence classes it has is finite. And so at some point, when you list all the equivalence classes, this list stops, right? So I have a finite number, let's say n, which is less than infinity. So let's just suppose that this is correct mathematical notation. So I have a finite number of equivalence classes. Right, that's it. Okay. So this is what the Myhill-Nerode theorem says. Now, are you ready for an anecdote? I have an anecdote to tell you. Okay, so what is the anecdote? So the Myhill-Nerode theorem was proved by John Myhill and Myhill-Nerode in 1957. So they wrote a paper together in 1957. So John Myhill died. He died in 1982, so I'm not going to talk about him. But Myhill-Nerode is still kicking it. In fact, he's 90 years old, and he's a math professor at Cornell. So you can imagine how lively and enthusiastic his lectures are. But the anecdote is that Prakash, so the original professor of this class, and I would say the one who teaches this class the best, he's actually Facebook friends with Myhill-Nerode. Okay. So the anecdote goes that whenever Prakash teaches his class, he posts this on Facebook, and he says, "Oh, I'm going to teach the Myhill-Nerode theorem with my class today." And then Myhill-Nerode, without fail, always likes his Facebook message or Facebook post. And then Prakash tells his students, and then he moves on. Okay, so I'm going to move on. That was the story. Good. All right. So let's go back to the serious business of proving this this theorem. Because I have this theorem, now how am I going to prove it, right? So the proof is going to be in 3 parts, 3-part proof. So what I'm going to do, because I'm saying that all these statements are equivalent, what I want to do is I'm going to say that 1 implies 2. I'm going to prove that 1 implies 2. Then I'm going to prove that 2 implies 3. And then I'm going to prove that 3 implies 1. And there's a particular reason why I'm doing it this way, because in the proof of 3 implies 1, there's a very remarkable result that I'm going to talk about later. Okay. So let's do the first proof. So the proof of 1 implies 2. Whoops. Come on. Okay. 1 implies 2. So what I'm going to do here, I'm going to do a direct proof. So I'm going to assume 1. I'm going to assume 1. In other words, I'm going to assume that I have some language L, which is regular, because it's accepted by some DFA. And I'm going to show 2. And so to do this, what I need to do is I need to find a relation R which satisfies all the properties in 2. right? Because the statement 2, all it says is I have some relation R and it has a bunch of properties. So I'm going to assume 1, and now I'm going to explicitly create this relation R and show that it has all those properties. And so it turns out, this is why we defined it at the beginning of class, that one such relation is if you set R to R sub M. Okay, and so let's see why. So let's see why. We need to sort of go through this list of properties that R should satisfy and check whether it does. Okay, so the first property that R should satisfy is that it should be an equivalence relation. Well, I know that R sub M is an equivalence relation. Hello, I know that R sub M is an equivalence relation. You can check that yourself, but it's a very easy check for an equivalence relation. Okay, so that's good. The other thing I need for statement 2 to hold is I need this relation R to be right invariant. Well, I proved that at the beginning of class. That's why I did it. So that's good. Okay. The last thing is the slightly more complicated condition, which says that if you take some of the equivalence classes of R, in this case R sub M, and you take the union of some of those, then you get L. Okay. Well, at this point, it's interesting to ask, and it's necessary to ask, what are these equivalence classes of R sub M? What do they actually represent? Well, let's consider this machine M, which we assumed in the hypothesis or in statement 1 accepts this language L. So I have this language L. I know that L of M is equal to L. Okay. Now remember what R sub M does. It's a relation on strings. It's a relation on strings. And in particular, it says that strings are related if and only if they go to the same state when M reads them from Q0. Okay. So perhaps I have some other state P, right? And I have I have some strings that all go to P. Then I have some other strings that maybe go to this state Q. And then maybe I have an accept state here, and I have strings that go to this state, this accept state here. So it turns out what R sub M is doing is it's partitioning the strings based on where those strings go in the machine M, right? Which I think is sort of intuitive, right? RM is sort of identifying pairs of strings. If those pairs of strings go to the same state, then you bunch them together. So then that whole bunch is just all the strings that go to the same state in M, from Q0, of course. Okay. So then if we ask, what are the equivalence classes of R sub M? Well, suppose I have some state Q in Q. So Q is the set of states of my machine M. Then one equivalence class, let's just call it S sub Q, right, is all of the strings in sigma star for which those strings starting at Q0 end up in Q, right? So clearly I have a partition, right? Because I have that no string ends up in 2 different states, right? So these are partitions, and their union is of course L, because I know that their union is of course sigma star, of course, because a machine can intake any string. And so in particular, if I take all of the strings that the machine can intake, then that's sigma star. Okay, so now remember what we needed to show. We needed to show that some of the equivalence classes of R sub M were equal to the language L. So let me venture a question. How can I write L as a function of S sub Q? Yeah, Bradley, yeah.
All the strings that go to the accept state.
Okay, good. So we're talking about accept states, but can you be slightly more formal?
Every element sigma star
Right, good, good. Yes, excellent. Excellent, very good, very good, very good, very good. So in other words, take all the strings in sigma star for which there exists a state, an accept state, where when you start at Q0 and you read X, the machine ends in F, right? Well, what's another way to rewrite this? Another way to rewrite this is we know that the the existential quantifier sort of maps to the union. So I can just rewrite this as it's the union of going through all the accept states and taking the union of S sub M. Okay. And so these are equivalence classes of the equivalence relation R sub M. I'm taking their union and I'm getting L. Right. So the only other thing to verify is that R sub M is a finite index. R sub M is a finite index. Okay, let's ask another question. Let's see. People seem awake. Yes? Very good. Excellent. Absolutely. Excellent. Very, very good. So the remark is, well, if the equivalence classes of R sub M sort of represent where the strings go based on the states of M, well, I know that M is a DFA, right? Deterministic finite automaton. And the finite there means that I have a finite number of states, right? And so R sub M is a finite index, of course, because M has a finite number of states. Good, excellent. And that completes this direction, right? Because I've started with 1. The only thing I assumed is that I had a machine M that accepted L. And I've shown that all the properties, that there exists a relation with all of the properties in statement 2. Okay, good. That wasn't so bad. Right? Okay. Maybe it was. No, I think it was okay. Come on. Yeah. Oh.
For 4, is that
Yeah. 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 So it turns out this isn't really true when you don't have a regular language, because if you have a language which is not regular, then you can't create a DFA with a finite number of states that exists. Good. Okay. Any other questions about this direction? No. Okay. Great. So let's do the other direction. The other direction is that 2 implies 3. So now I really need to remind you what 2 implies 3 says, because now it's been like 10 minutes, so you've probably forgotten the theorem already. So what we need to do is, again, we're going to show this directly. We're going to assume 2. We're going to assume 2. Okay, so what does 2 say? 2 says that there exists some relation R, which is an equivalence relation. It's right invariant. It has a finite index. And the union of some of its equivalence classes give you L, right? That's what 2 says. So I'm going to assume that that's true. And what I'm going to do is I'm going to show 3. So in other words, I'm going to show that the index of the Myhill-Nerode relation is finite. So this Myhill-Nerode relation has finite index. Okay. So to do this, I'm going to use a nifty trick. I think it's quite nifty. I'm going to show that the index of the Myhill-Nerode relation is less than or equal to the index of that relation R, one of the relations R that satisfies 2, right? So of R, where R satisfies 2. Okay, so why will that have shown that the index of the Myhill-Nerode relation is finite? Well, I know by assumption that the index of R is finite, right? So if I have a number that's less than or equal to a finite number, then of course that number is defined. Okay. So the tricky bit here is, how do I actually do this? Well, let's consider the equivalence relation R, right? So I have my equivalence relation R. So I know it's an equivalence relation. I know it has finite index. So that means that it has a finite number of equivalence classes. Maybe these are the equivalence classes, right? So this is 1, this is another, this is another, and this is maybe the last one. But I have a finite number, so this list ends at some point, right? Okay. And now let's consider the Myhill-Nerode relation. So let's consider the Myhill-Nerode relation. So because I already know that it's an equivalence relation, I know that it has equivalence classes. So namely, it has this equivalence class, it has this equivalence class, and so on. And now I'm not quite sure whether it has a finite or an infinite number of equivalence classes. So I need to show this. Well, the way I'm going to show this is I'm going to say, take any pair of strings, x, y. So take any pair of strings, maybe it's the pair of strings which is in this equivalence class. What I'm going to do is I'm going to show that this pair of strings is necessarily related via the Myhill-Nerode relation. So in other words, I'm going to say that if x and y are related via R, then it must be that x and y are related via the Myhill-Nerode relation. In other words, I want to show that this pair of strings has to go together into one equivalence class xy. Okay, well, that's not that helpful, right? Well, no, actually it is. Why is it helpful? Because now I've considered an arbitrary pair of strings, xy. I've said that they were related. So now it wouldn't have mattered had I picked this pair of strings or this pair of strings or this pair of strings. Any of these strings will actually fit inside this equivalence class. But you could say, right, nothing's stopping me from saying that, oh, maybe for the pairs of strings that are related in this equivalence class also fits into this one. So in other words, I have a many-to-one mapping. Right? I have a many-to-one mapping from the strings in the equivalence classes of R to the strings in the equivalence classes of the Myhill-Nerode relation. So if I have this many-to-one mapping, then that means that I must have a larger number of equivalence classes from R than from the Myhill-Nerode relation. Because if you picture it a different way, so let's picture it a different way. This is sigma star. This is sigma star. Right. Now consider the equivalence relation R. Right. So the equivalence relation R is very sort of fine-grained. So it partitions sigma star very carefully. Very carefully. Okay, so it's very careful in its partitioning. Right. So it's a very fine-grained or very refined partition of sigma star. Now, what we're going to do, we're just going to say that the equivalence class, the Myhill-Nerode relation, has equivalence classes which are coarser, right? So they're less fine-grained. In other words, the equivalence classes of the Myhill-Nerode relation are maybe this partition. Let's see. This partition. Okay. And everything else. So hopefully now you're convinced, well, I started with, I don't know how many, maybe 10 equivalence classes. But now, because I know that this equivalence relation is coarser, right, I only have 3. So of course I have an index which is smaller than the index I started with, because that index was finite. Then the other index must also be finite. Yeah, good. Okay, so now I actually need to convince you. This was sort of pictorial. This is what I'm actually doing. But now I need to convince you that this is true slightly more formally. And so to do that, the only thing I really need to do is I need to show you that if I have a pair of strings which are related by R, then that pair of strings must be necessarily related via this Myhill-Nerode equivalence relation. So that's what I'm going to do here. Okay. So suppose I have a pair of strings, x, y, and sigma star. And suppose that x is related to y via R. This R is the one that satisfies statement 2. Then what I want to show is that x is related to y via this Myhill-Nerode relation. Well, what does this mean by definition? By definition, that means that I alternatively want to show that if I take any string in sigma star, and I stick that string to x, and I stick that string to y, then if xz is an L, it must imply that yz is an L, and vice versa. That's what I need to show. Okay, so in other words, I need to show this if and only if at this point. So this is an if and only if. I'm going to do the forward direction. Again, this could have been just a sort of if and only if proof. but I want to be slightly more explicit. But the backward direction is going to be exactly the same. Okay, so what I'm going to do is I'm going to prove the forward direction of this if and only if. So how am I going to do that? Well, now let's pick some arbitrary string z. Pick some arbitrary string z in sigma star. Okay. Now let's say that xz is an L, right? So it satisfies this premise here, Okay. Now, what does this tell me? Let's see. I'm going to venture a question. What does this tell me? Let's think about it. So I know that a string is an L, right? And so I know that the hypothesis is true. I know that statement true is true. In other words, I know that I have a relation R, which is an equivalence relation and has a finite index. And oh, maybe this would be important. The union of some of the equivalent classes gives you L. Maybe not one. Come on, someone else. Come on. Take a shot. Yes, correct. Me, although we've already answered.
So, the x of z, xe, then also q0 xe is.
In simple terms, what do we know about xz in terms of the equivalent classes of R?
The input after xe.
That's not quite what I'm looking for. But I think you're saying what I'm looking for, but not in the words that I want. Yeah. Yes, good. So okay, I maybe made okay, yes, very good. Yes. Okay, so let me back up a second, but maybe that was one leap too far. Okay, so let's back up a bit. So I know that xe is an L, right? So that means that I know that xe is in an equivalence class of R that makes up L. Now, as someone just said, that implies that YZ must be in the same equivalence class. This implies that YZ is in the same equivalence class. Why does this imply? Why is this implication true? Yes, very good, because R, very good, excellent. Because R is right invariant, excellent, very good. So I know that YZ and XZ are in the same equivalence class, but this equivalence class made up L, right? And so that means that YZ is also in L. So that means that YZ is also in L. Okay. And so that's exactly what it means for X and Y to be related by the Myhill-Nerode relation, right? So I've started with from string X, and I've taken some arbitrary extension Z. I've stuck it to X, and I've shown that if XZ is in L, then YZ must also be in L. So that proves the forward direction, and then the backward direction is exactly the same. Good. Okay, I have a thumbs up. Wow. Good. All right. So what this shows then, right? This just shows that if X and Y are related by R, then X and Y are related by the Myhill-Nerode relation. So in other words, the Myhill-Nerode relation is coarser than the relation R because it sort of contains one or more of its equivalence classes. The equivalence classes of the Myhill-Nerode relation, that is. Okay, so that completes 2 implies 3. Okay. Now, for my last trick, I'll do 3 implies 1. Okay. But before that, any questions? Oh, yes. Yeah. Oh, good. So why is YZ in the same equivalence class? Good question. That's like the crux of the proof, so I'm glad you're asking. So I know that XZ, wait, let's do this. So this is an equivalence relation of R, right? I know that XZ is in an equivalence relation of R, right? But I know that R is right invariant, right? So that means that YZ must also be in the same equivalence class, right? Yeah. Related, because X and Y are related from the premise, yes. From the premise here. Yeah. Because I already know that X and Y are related, right? I already know that X and Y are related, and I know that XZ is in some equivalence relation. So then by right invariance, YZ is also in the same equivalence class. Yeah. Oh, well, in other words, really what I'm just saying is I'm just saying that let's see, I don't want to get this backwards. Right. What I'm just saying is that in the loosest possible terms, the relation R is kind of a subset of the Myhill-Nerode relation, right? So if you take some of the equivalence classes of R, then they're together in the same equivalence class of the Myhill-Nerode relation. So R is much sort of more fine-grained, and the Myhill-Nerode relation is much more coarse, right? Because it sort of captures more space. Right. Maybe let's talk after thoughts. Yeah. It's a very subtle point. Yeah. Let me move on. And then, yeah. Okay. So 3 implies 1. What does 3 implies 1 need for it to be proved? Well, I need to assume, in other words, what I'm going to do is I'm going to assume that the Myhill-Nerode relation has finite index. So assume that this has finite index. Okay. And what I need to show that there exists some DFA M such that the language accepted by M is equal to L. So in this last trick, what I'm going to use is I'm going to use a trick from Tuesday's lecture when I take equivalence classes and I make those equivalence classes states of my machine. That turns out to create a machine M which accepts the language L. And so I'll prove that in a second. So what I'm going to do is I'm going to create a DFA M prime, which will look like Q prime, sigma, delta prime, Q0 prime, F prime. Okay. Based on the equivalence classes of the Myhill-Nerode relation. So in other words, Q prime, I'm going to assign Q prime the equivalence classes of the Myhill-Nerode relation. So to be slightly more formal, this is sometimes written as sigma star. So you take the universe, or you take the set on which the relation is applied to, quotient the relation. So this is just the same thing as this. So that's what I assign Q prime to. Then the start state, Q0 prime. Well, what I know about DFAs in general, I know that the string that, regardless of the machine, always ends up in the start state is the empty string, right? And so a natural representative for the equivalence class that represents the start state is the empty string. So what I'm going to say is I'm going to say that Q0 prime is the equivalence class of the Myhill-Nerode relation, which has as representative the empty string. And this becomes obvious when I prove why this machine is correct. But for the time being, the intuition is just that I know that the empty string always starts and ends at the start state of any machine, any DFA. So that's the intuition. The before last thing is defining the set of accept states. So for the set of accept states, this is also not going to be that tricky. I'm just going to say, take all the strings that are in L, and then use them as the representatives of the equivalence classes. And those equivalence classes are going to be the accept states. The last thing is, how do I actually define a transition function for M prime? Well, the transition function delta prime is going to accept a state. A state is simply an equivalence class with some representative x. And as its second input, you have a letter A. So what delta prime is going to return in this case is just going to say augment the, well, use as representative to the equivalence class x concat with A. So the intuition here is just, you're extending the string x with that input letter A. And so you might be asking yourself, wait, is this really well defined? Because I've sort of defined this machine, maybe some would say arbitrarily. This is definitely well defined. There might be one problem. The only one problem would be, I know that to transition from one state to another, I have to look at equivalence classes of the Myhill-Nerode relation. But those equivalence classes have representatives, right? So in this case, I picked as representative x. But what if I had picked as representative y, right? Then this transition function tells me that if you get as input A, then you'll return ya. Okay. But it turns out that these two things are the same. Why are they the same? Right invariance, very good. So this is okay by right invariance of the Myhill-Nerode relation. Good, excellent. Okay, so now I've somewhat arbitrarily created this machine. Now I need to show you that it's correct. So the first claim to do this is a claim that's proved by induction, and so I'm going to skip it because it's very boring to prove this by induction. But the claim is that the extended transition function of my machine M prime, if it takes as state the equivalence class with representative x, and it takes the string y, then what it's going to do is it's just going to sort of concat along the sequence of letters in y. So it'll take the first letter of y and concatenate it to x, the second concatenate it to x, the first letter of y, and so on, right? And so in the end, what this will give me is the state with representative of the equivalence class xy. And this is fairly simple to prove by induction. So this proof is by induction on the length of y. But I will not do that because that would be torture for both me and you. Okay, good. So that's the first claim. That's claim one. Now claim two. What is claim two? Claim two is claiming the correctness of the machine. So in other words, it's claiming that the language accepted by M prime is equal to L. Okay, so I need to prove this. I'm going to, of course, use claim one to prove this. How am I going to do this? Let's suppose I have a string x, which is accepted by my machine M prime. So in other words, x is in the language accepted by M prime. Then by definition, this means that if the machine starts at Q0 prime, its start state, and it reads x, then using its extended transition function, so notice the delta prime here, it will end up in an accept state F prime. Well, now let's just rewrite this as the sort of explicit 5-tuple, right? So let's just replace what each of these things should be. So delta prime can stay the same, but Q0 prime is just the equivalence class with representative the empty string. Then I have my input string x, and I have F prime. What is F prime really? Well, it's the set of equivalence classes for which the representatives of those equivalence classes are in L. Okay. So now what I'm going to do is I'm going to use my claim, which I've claimed without proof. I'm going to use my claim, and I'm going to go from this to saying that really this is the same as taking the empty string and sticking all of x to the empty string. So this is the same as saying I end up in state empty string concat x, which is in, it's annoying to rewrite, but which is in here. Okay. Well, I know that if I concatenate the empty string with any other string, I just get that other string. And so that implies that this equivalence class is part of this set of equivalence classes. And so by definition, that means that X is in L, which proves the correctness of the machine. Okay. Yeah. Any questions about this? No. I have another anecdote. Wait, let me tell the anecdote. So, do I have time to give you an anecdote? No, not really, but I think it's funny. Last year, Prakash had to go on a trip, and when he went on the trip, he picked his flight at a time which was sort of conflicting with the class time at 3:30 because he doesn't really care. And so he asked me to fill in for him, and so I guest lectured. So that was my first guest lecture at 3:30. I was very excited. And what had happened is I was planning on giving it with the iPad, but then I had tried to connect it to the projector and that failed. So then I started to panic. And then I tried to use this dog cam thing, which is sort of this prehistoric thing that allows you to project a piece of paper onto the projector. And that also failed. And so I ended up using the Blackboard, which actually turned out to be quite fun. So I'm doing the Blackboard thing, I'm proving this, and everyone's very excited, as you are. And I turn to look at the students, and maybe like right next to where you're sitting, I look at a student, and she's completely confused. And I was like, ah, so that's what exciting about lectures. That's the anecdote. Maybe less funny than the other one. Okay, good. And so what we've done, we've shown that 1 implies 2, 2 implies 3, and 3 implies 1. And so we've proven the Myhill-Nerode theorem. So this completes the whole proof of the theorem. Good. Okay, so now I'd like to remark something. I'd like to remark something which will bring us to the uniqueness of minimal DFA. So this remark here, this remark is that remarkably, so this remark is remarkable. Remarkably, M prime was a minimal DFA that accepted L. Isn't that remarkable? I think that's pretty remarkable. So I'll put an exclamation mark. That's how remarked I am. Okay. So I need to show this, right? I need to show this. But it's not really a coincidence. This is what sort of Myhill and Nerode were aiming at when they devised this theorem. But before I show this, I can take a question, and I'll take a question from Owen. Yes.
Why do we go?
You could have called it M. It's M prime is just, yeah, I just didn't want to confuse the notation. So the question is, why did we use M prime instead of M? But M prime is just the name of some DFA that accepts L. So I could have used M or M prime, it doesn't matter. That was the proof for 2 to 3. In 3 to 1, you no longer are concerned with R sub M. So you don't think of it. Yeah. Okay. So what I want to do now is I'm going to state as a proposition. So in case you don't know, a proposition is like a theorem, but slightly less important. So I'm going to state as a proposition this remark. So the proposition says that the DFA M prime from the proof in 3 to 1 was a minimal DFA. Okay. So I need to prove this. The proof is also remarkable. So the proof of this proposition is, well, let's consider some DFA M. What I want to show is if M accepts the same language as M prime cannot have less states than the machine M prime. Okay, so consider some DFA M such that the language accepted by M is equal to the language accepted by M prime. Now recall for a second, recall the equivalence relation R sub M. Okay, so keep it in your head. Remember about R sub m. Okay, so store it in memory. Now remember what we did in the proof of 2 implies 3 is we showed, so in the proof of in 2 implies 3, we showed that any relation, we actually showed that any relation are satisfying 2 satisfied the following thing, where the following thing was that the index of R was less than or equal to the index of the Myhill-Nerode relation. Right? This is what we showed back 20 minutes ago in the proof of 2 implies 3. Okay. Well, one such relation which satisfies the properties in statement 2, or the properties of R, is R sub m. Right? Now remember, what does the index of R sub m represent? The index, so the index of R sub m represents the number of states of m. Okay, so I have the number of states of m. Now, remember, what is the index of the Myhill-Nerode relation? Well, the index of any relation is its number of equivalence classes. But by the way that we constructed, the machine M prime, right? We said that Q prime was the equivalence classes of the Myhill-Nerode relation. And so, in other words, the number of states of the machine M prime is equal to the index of the Myhill-Nerode relation. So in other words, the index of the Myhill-Nerode relation, well, this is equal to the number of states in M prime. Well, this inequality still holds, and so I have that the number of states of M is less than or equal to the number of states in M prime. Or no, greater than or equal. So the number of states of M is greater than or equal to the number of states of M prime. Right? And so by definition, M prime is a minimal DFA. Okay, excellent. That's quite a remarkable proof. I think you have to read it over twice to make sure that you're really remarked. See, I've been wrote in my notes amazing. Maybe I'm not conveying that well enough. No, I think I am. Okay, any questions about this? No, doesn't look like it. Okay. So then there's an immediate implication to this proposition. The implication of this proposition is given a regular language L, the number of states in a minimal DFA M such that the language accepted by M is equal to L is the index of the Myhill-Nerode relation. So that follows immediately from the proposition we just showed. And so now I'm ready to talk about the uniqueness of the minimal DFA. So it turns out that when you have a minimal DFA, any other DFA which is also minimal and which accepts the same language is going to be the same. And it's slightly tricky to prove that if I just show you the minimization algorithm. It's a bit difficult to prove. But now that I have the Myhill-Nerode theorem, and in particular, now that I have the construction of 3 gives you 1, right? So that DFA, which turns out to be minimal, it's quite easy to show that given any other minimal DFA, that other minimal DFA is exactly the same as M prime, the one that we defined in 3 implies 1. Okay. So the proof of that is like 30 minutes, and I clearly don't have 30 minutes, but I do have a video about that, and so I will post that. But what I want to do in the time that I have remaining is to sort of state the conclusions of that result. So let me sort of write down what I just said. So we can use can use the construction of 3 implies 1 to show that minimal DFA are unique. So i.e. take any minimal DFA M such that the language accepted by M is L. And so we will show in the proof that I'll post, we'll show that it is, so this minimal DFA M, it is the same as M prime, so the one based on the equivalence classes of the Myhill-Nerode relation. So now, if you're mathematically inclined, such as I am, you might be thinking, well, this statement sounds a bit fishy. What do you really mean by the same? So what does it mean for 2 DFA to be the same? That's a great question. He asked himself. So I'm going to define that right now. So I'm going to define what it means for 2 DFA to be exactly the same. Okay. And so this notion, which is common throughout mathematics, is known as isomorphism, right? So that's when you have 2 mathematical objects, and when they're exactly the same, you just say that they're isomorphic. Okay. So you might have seen that in linear algebra when you talk about matrices and linear operators. Okay. Or also in graph theory. Or any other math. Okay, so 2 DFAs, let's call them M. And let's write them out explicitly. M and M prime. Are isomorphic. So they're isomorphic. In other words, they're the same. If there exists a bijection, so I hope you remember what a bijection is, from the set of states of M to the set of states of M prime, such that the bijection satisfies the following properties. The bijection maps the start state of M to the start state of M prime. The bijection also, given an accept state of M, maps it to an accept state of M prime. So that's the first and second property. And the last property is maybe the most funny looking one, is if you take the output of the transition function when it's given, let's say Q and a letter A, and you map that with the bijection, then this will be the same as if you had initially mapped Q with the bijection, you had read the letter A, and then you had used M prime's transition function. Okay. So this is what the bijection must satisfy in order for these 2 machines M to be isomorphic. Now, again, this looks like gibberish, right? What does this really mean? Let's look at a picture. Let's look at a picture, and let me also give you sort of a natural language explanation. So what this is saying that M and M prime are the same. So, the same is the layman's way of saying isomorphic. If there exists a relabeling function, from states M to M prime. So for example, suppose I have 2 machines, M and M prime, and I have the machine M, which looks like this. And the machine M prime, which looks like this. Okay. Whoops. So what I mean by there exists a relabeling function is there's a way of relabeling the states. There's a way of relabeling the states of the machine in M prime, in M, such that it looks exactly like the machine M prime. So for instance, the relabeling function in this case, have a nice day.
You too.
Oh, thanks very much. So the relabeling function in this case is taking the state Q0 and mapping that to S1, and taking the state Q1 and mapping that to the state S2. Because if I do that, then clearly I've recreated the machine M prime. So of course, M and M prime are the same. Good. Okay, so that's what it means for two machines to be the same or isomorphic. I have this relabeling function such that I can make M look exactly like M. That's all. Okay. So now I can state the proposition which actually says that minimal DFA are unique. So proposition 2. Given a regular language L and the minimal DFA M prime that I constructed in the proof of 3 gives you 1, from 3 gives you 1, any minimal DFA, any other minimal DFA or any DFA, right? It could be the same, is isomorphic to M prime. Okay. So the proof of this is a bit tedious. I will omit it, but I will post a video. But essentially what you need to do is you need to take any other arbitrary machine M, which is minimal and which accepts the same language as M prime, and show that there exists this relabeling function. So there's a way of making that machine M look exactly like M prime. And so once you do that, you know that minimal DFA are unique. Okay. And so this is very relevant for your assignment question. In particular, it's relevant for assignment 2, question 5. Because what this tells you now, this tells you that if you create a minimal DFA M, where M is a 5 tuple. So if I create a minimal DFA M, then if I start at the start state of my minimal DFA, and I read some string X, and I end up in state Q, well, this is exactly the same as saying that in the minimal DFA of M prime, so this construction from 3 to 1, if I start in its start state, and I read X, then I end up in the equivalence class with representative X. So this is going to be very helpful for you to solve assignment 2, question 5, in particular part B. Okay, good. So with the 3 minutes that I have, I can show you an algorithm that does something very interesting. So the last thing I want to show you is I'd like to show you something by remarking something. It's that if I take the minimization algorithm plus this result that I showed without proof, unfortunately, that minimal DFA are unique, then I have the ability to create decision procedures for decision problems about FAs and regular expressions. Okay. So I'm gonna show this to you in a second. I'm gonna show this to you by giving you an example. So suppose the decision problem I have in this case is given 2 regular expressions, R1 and R2. Is the language described by R1 exactly the same as the language described by R2? Okay, so this decision problem seems at first a bit tricky, right? So one naive way of trying to solve this is, let's make a for loop, right? The for loop goes for x in sigma star, right? Check if x matches R1 and R2 at the same time, right? Well, in other words, check if the match, so whoops, the match of X with R1 is equal to the match of X with R2. So this is a naive way of doing it, a brute force way of doing it. This is not going to work. Why is this not going to work? Because this for loop is infinite, right? So that's not good, right? You shouldn't be able to run a computer program forever. And so what you can do instead is you can do the following thing, which will be helpful for solving assignment 3, question 1. So you can say, well, I have two regular expressions, R1 and R2. Now I know that I can convert the regular expressions R1 and R2 to FA. So I can convert R1 to an FA M1 and R2 to an FA M2, right? So maybe it's an NFA. So we didn't explicitly show this in the regular expression class, but the idea is you just build on top of the closure properties to sort of combine the FAs of the atomic regular expressions into the more complicated ones. So I'll get FAs, they'll probably be NFAs. So I'll get two NFAs. Then I can convert through this sort of subset construction NFAs to DFAs. So I get M1 prime, this is a DFA. I get M2 prime, this is a DFA. Right? So now M1 prime and M2 prime are going to look quite different. So now let's try to minimize them. So let's minimize them, M1 double prime through the minimization algorithm, and M2 double prime through the minimization algorithm. And now what the result I just showed tells us is that since minimal DFA are unique, all I need to do now is I just need to check whether the machine M1 prime is exactly the same as M2 prime. So whether I can sort of map states from one machine to the other, and I can just do that in a brute force way by sort of matching every state of by checking every possible match between M1 double prime and M2 double prime. So then I can just check if there is a bijection. If yes, then R1 and R2 do describe the same language. If no, then they don't. Okay. And so something like this is what I expect from you in assignment 3, question 1, which I will release on Thursday. Thanks very much. Have a nice weekend.
Hi.
Hello.
How are you doing?
I'm very good. How are you?
Pretty good.
Excellent. It's good to hear.
Thanks. I had a question.
Yeah.